All right, I'm sure more people will be filing in. It looks like we've got quite a few already, but let's go ahead and get started with some introductions. So I'll start. I'm Dr. Jacob Nectarline, material science background, but I'm now CEO and founder of Elementum 3D. We kind of put this series of presentations together with Bowler, who are here as well, and we like to bring on subject matter experts, which is why we brought in Judith from NREL. I'll let each of you kind of do a short introduction of yourselves, and then we'll kind of go into the outline of what today's going to look like. Uh-oh, did we just lose Judith? We'll start with Judith. If you'd like to give us a short introduction and background on who you are, and then we'll go to Greg and then Thomas.
Yes, hi. I'm Judith Vidal, and I did my PhD at Colorado School of Mines, and that's nice to see that a lot of people here is from that university. So yeah, I'm a materials person by design, if I say that. I'm a manager at NREL, the National Renewable Energy Laboratory, in the buildings area, but I've been working a lot in the CETO office for CETO office projects, study for the Solar Energy Technology Office in the thermal energy office, thermal energy technology that is concentrating solar power. So very happy to be here to show you what are those projects that I'm trying to incorporate nickel alloys printed.
Greg, if you'd introduce yourself next.
Sure. Hi, my name's Greg Chitwood. I'm also a Colorado School of Mines graduate, Judith, although I think quite a long time ago. I have about 35 years of experience in oil and gas. I worked for Halliburton for many, many years, but in 2016, I joined as a metallurgical consultant for Bühler Edelstahl, where I've been happily consulting for them now for going into my 6th year.
Excellent, thank you. And Thomas?
Well, hello everybody. My name is Thomas Lucas. I'm sitting right now in Austria, right in the steel mill of Bühler Edelstahl. I am a material scientist, so actually I graduated in June this year, so I can't compete with the other guys' experience, but hopefully I can give you a nice insight on our powder production today. So yeah, looking forward to it.
Great. So let's go ahead and dive into, I've got an introductory presentation here, and then we'll get to the other presentations as well. Please, we'll have questions at the end of each presentation, and we'll kind of go through and just kind of have a discussion at the end of each presentation, maybe 5 minutes of questions and discussion. If anyone has any questions, feel free to send a message. There should be a method in which you can send in questions under the questions panel on the right panel here. So please send those in and we can kind of address them as they come. And then there'll be some time for some general questions at the end where the entire panel will participate. But we'll start with a quick overview of what we've been doing at Elementum and some of our impetus for having this presentation and really getting into the presentation, and we'll kind of go from there. So to start, as I mentioned earlier, I'm Jacob Nectarline, material scientist, and that's really what I'm going to cover a lot of today is some of the material science we've been doing at Elementum. We've been focusing a lot on the past on aluminum alloys and hot tearing and hot cracking in those alloys, but there's similar difficulties and problems in nickel superalloys. And so over the past 4 years, we've been doing a lot of development in the nickel alloy space. And so we're finally ready to really present that and really start talking about some of the really exciting things that we've kind of run into. To give you a little bit of background on who Elementum is, for those of you who don't know, our goal and our mission from the beginning has been to expand the materials selection. So opening up that materials library to the additive manufacturing world, specifically the laser powder bed side of things, but we've been getting into some other areas recently as well in blown powder DED, and then also wire fed materials as well. We're located in Erie, Colorado, just north of Denver a little ways, so hence the quite a few Colorado School of Mines graduates at our facility. But I think there's a Some exciting things that we have coming down the lines as far as an announcement soon about a new facility, much larger facility, and also announcing the completion of our latest funding round as well. To give you a general overview, these are the materials that we have listed on our website that are available to purchase today. But I did want to highlight some of our nickel alloys, which are new and haven't really been exposed to the market for very long as far as actual having data, having customers, and so it's exciting for us to be able to talk about those and really get to dive into those. Specifically, the Inconel 718 and 625 Ram 2 variants, which we'll get into in a minute. But also there's been some recent, I think, really exciting results with a customer of ours on our Rene 80 Ram 1 products. So I first want to start with why 3D printing? What's the point of 3D printing? Why wouldn't you just machine this out of a block? Why wouldn't you investment cast these materials? And I found 3 real business cases so far for additive manufacturing and why you'd use 3D printing. And then there's one that's coming soon. And so I put that over there as coming soon. Lightweighting and removing bulk. That is a business case. And in nickel alloys, because they're heavy, there's benefit to that in some industries. That's typically, something that you tack on as an added benefit, but is not normally a driving business case. The first big driving business case is printing designs that you couldn't otherwise. So cooling channels that hug contours, manifolds that can direct fluids in different ways, whether you want them to be turbulent, maybe you want them to be laminar in some areas. You can have it open up and close down very easily with additive manufacturing, and you can have it swirl, all sorts of different things. The other one that I think is really exciting and has been exciting recently is combining components. So being able to combine parts into a single component. That's exciting for a number of reasons, but the example I give is there's an application that's been in development for an engine that was 900 parts, and they're able to reduce that down into 20 components. And so if you're talking about an engine that was 900 parts, imagine the repair guy who's out there on the tarmac who has to keep track of those 900 components. Same for manufacturing. If you're talking about taking 900 components and bringing them down to 20, the supply chain and logistics is so much more straightforward. So there's some big advantages there. And then coming soon is logistical improvements and point of use manufacturing, those sorts of things, which I think could be very interesting for the oil and gas and automotive worlds. So a little bit of background on what makes Elementum different in this case for our nickel superalloys and what we're doing that's different. We're using a technique we've called reactive additive manufacturing. So we're forming ceramic particulates for nucleation benefits, for equiax grain benefits, for grain size reduction by using a chemical reaction during the printing process. So you use an off-the-shelf printer, and then you spread powder just like you would any other laser powder bed printer. And then there's a chemical reaction that occurs during the laser melting process, which forms these precipitates. And there's a number of different benefits to that, from spreadability of the powder to a number of other advantages on the actual products of the mechanical properties of the parts. There's a lot here, and I'm not going to unpack all of this, but to say that chemical reaction forms these particulates, the thing to really key in on is that it makes some metals that are unprintable, for the same reasons that they're unweldable, printable. And so there's advantage here of it opens up the capability and opens up our availability of a lot of these difficult to print alloys because of this technique. So why? What's the point? Why? I mean, you're changing the alloy. Why not just try and print it? The problem is that you get these columnar grains. Now, this is an extreme example in aluminums where you get these columnar grains that ultimately tear apart and fail. In nickel alloys, we typically see much less catastrophic results. We see, but yet, still making it completely unusable. But the catastrophic results really tend to be, you have these columnar grains that aren't well adhered to the grain next to it. So you get very different properties in the X versus the Y. And in many cases, you get cracking between those grains. in a lot of these alloys. So the difference here is when we add these nucleation sites, we can actually form materials that you couldn't otherwise, and we get properties that are very similar in the vertical to the horizontal. And then in addition, we get the benefits of these ceramic particles distributed throughout the metal, which we'll talk about here in a minute as well. But you can kind of see the progression of as we add more ceramic, the grain size of that material decreases. And so I think that's an important, at least discussion point here, is the refinement of those grains. We might see really small cracks with no material at all in some of these very hard to print nickel superalloys. But as we add our reaction synthesis products, we're seeing much smaller, much more randomly oriented grains. You see these very vertical grains where the cracks can form in between them to much smaller grains. Now, what are we doing with this? There's a number of projects and public projects that we have going on right now, both with, we completed a project with the National Science Foundation on developing high temperature alloys. That's where the Rene 80, the MAR 247 product has really got its start and really got going. We have a current Navy project that we're working on right now in controlling the nucleation and microstructure of different alloys that we had not worked on in the National Science Foundation project. And then with NREL, which I'm sure Judith will talk about here in a little bit, we've been working on some very high temperature, very high corrosion resistant materials at those temperatures that just aren't printable otherwise. And so we'll kind of get into that in a minute. I won't go too far into each one of these that I have, but suffice to say, if you look at the properties, we're getting double the yield strength by adding 2% ceramic. We're also getting the same yield strength in the XY as we are the vertical, and it's because of these kind of particulates. So I want this to kind of sink in as whatever nickel superalloy that you're looking at, there's potential benefit to, well, you can get better strengths, you can get better high temperature strengths, you can still maintain ductilities with this particular technique that we're doing to a lot of different alloys. Our most recent work has been in Haynes 230 alloy, where we're modifying that alloy with our inoculants, and we're seeing a lot of different benefits. So you can see some cracking here on the left. It might be difficult to see, but you can see these kind of cracks that are running through. That goes away, along with a lot of the porosity that we would typically see that can be caused by the same kind of columnar grain structure. And that holds true through a lot of different alloys, from Waspaloy, Rene 80, C276 and the 247 have been a lot more difficult, but we've seen some really exciting results recently, and hopefully we'll have some data to share here in the next few months on that particular alloy system, because I know there's a lot of interest in it. Once again, we're just seeing benefits and differences in these materials. So if you want to see information and data on a particular alloy, let's dive into it. But one of the things I did want to highlight here is that we're maintaining our ductility in a lot of these cases, where we're even seeing improvements in ductility compared to the wrought alloy alone when we're going to elevated temperatures. And so there's some benefits and some behaviors that are occurring that are beneficial that you might not even see with the raw alloy on its own. So we're not just matching the alloy that existed, but we're also looking at improving upon that. Same with the Rene 80, as I mentioned. There's a customer of ours that has recently had a lot of success in Italy, and they just put out an article about it, and I think there's a lot of excitement around this particular material in the US as well. So that's us. If there's any questions, I'm happy to take them now. And then next up, we're going to bring up Judith to talk a little bit about what NREL is doing with additive manufacturing and new materials. Okay, so it looks like the first question already has an answer to it, so we won't go there. But if maybe there's difficulty in figuring out the question system here, since we don't have a way of being able to turn on. Fatigue is a question. So we have seen some fatigue improvements. I'll start with, because we have more data in the aluminum alloys, we've seen some real interesting results with fatigue improvements in the in that system, in that we're seeing almost a pseudo fatigue limit in aluminums, which is not typical. We're also seeing better fatigue numbers as well, and it's almost as if the crack resistance has improved because of those particulates, and because those particulates are so small, they don't act as a crack initiator either. So we have seen some benefits in the nickel superalloys as well. I apologize, I'm trying to figure out the question system myself. So if anyone sees some questions and wants to jump in, feel free. Thermal stability, that's a question that we see a lot. So that's something that we're continuing to study and look at, but we start with looking at the different thermochemical models of, are these ceramics stable? What is the stability at particular temperatures? And so we're specifically designing the ceramic systems that are in them for these particular alloys, but we're also studying the results, because you can model things all you want, but ultimately you really need to study the actual system itself and do some different studies and tests. And so that's something that we're continuing to do, because there are so many different environments that these materials can be exposed to, whether that's typical room temperature up to 800 degrees Celsius for a lot of these nickel alloys, up to 1100 and higher Celsius for some of them. So yeah, we're doing testing at all of those temperatures. Let's see here. Let's go ahead and go on, and I can come back to some of these questions later on in the at the end of the presentations. But let's go ahead and bring up Judith so that she can kind of talk a little bit about what's going on at NREL. So hand it over to Judith here.
Okay. Can you hear me and see the presentation?
Yes. Yes, we can.
Okay, great. Well, thank you. It's really appreciated that you invited me for this this meeting, and it is nice for me to show you what are the approach that we're taking right now at NREL, that is the National Renewable Energy Lab. The technology that I'm going to be discussing today is concentrating solar power, that we call CSP. And there are several of these big, humongous plants that the solar field can be maybe 1 mile of a diameter. And this is a photo that you see at the top that is a bright, that is the receiver, solar receiver. So what we have is our heliostat are putting to the focal point on top of the tower, and then we're able to concentrate the heat that is coming from the sun. So I'm going to be explaining you what the technology is about and what are the challenges and opportunities that we see here for advanced manufacturing. So the project itself, that it is funded by the Department of Energy, the CETO office, that is the Solar Energy Technology Office. The title of the project that we are working with Elementum 3D is Advanced Manufacturing of Nickel Superalloys for the 3rd generation of CSP. The growth of the CSP worldwide, as you can see here, is growing dramatically. And the data that I was able to find was up to 2019, and then you can see here what are those that are being under construction. A lot of those are in China and the Middle East. And of course, you need places and zones that are really have a good solar resource. Here in the US, we were having some of them, but they are mostly in China and the Middle East. Here is, on the left, is how it works and what is the advantage that we have for this type of production of electricity. These plants are to produce electricity and are CO2 free. So what you can see, and let me try to see if I have a pointer here. Yeah, here is what we call the heliostat. There are a lot of mirrors that they are at a certain angle, and then they're going to be just concentrating the light here on the top. That is what we call the solar receiver. The solar receiver, then we have fluids that are coming from a cold tank going up, being pumped up to the receiver. It will be absorbed, the heat that is being concentrated here, and then it will go, and sometimes it will be as a storage, it will be stored in a hot tank. And I'm sorry, and then these two are going to be really going, these fluids are going to moved to power cycle. The current temperatures that we have for electricity production right now that are commercial plants are the Rakim cycle, and we're trying to move for the second generation to the supercritical CO2 power cycle. So these are, for example, that we can try to have from 50 megawatts plant size to 200 or 150 size of megawatts. Of course, the size of the plant, depending on this production, is going to be depending on the solar field. And the solar field is also, the size of the solar field will be it depends on the amount of electricity that you're producing and the amount of storage in hours that you want to do. In this case, the one that I'm showing you here is for a base load power and with 12 hours of storage. So here is how we call about the base load. So at the beginning in 2010, for the second generation, we were at a 21 cents per kilowatt hour of production. And now in 2019, we were able to drop it to 9.8, but the goal for 2030 is to reach the 5 cents per kilowatt hour. So here is also how you can see for each of the different portion of the plant, what are those metrics and targets that we need to meet in order for us to really drop the cost to 5 cents per kilowatt hour. So in this one, that is for the generation, the third generation, what we're trying to go here at the exit temperature at the receiver is 720 degrees C. And the inlet temperature, that depends on the fluid itself. Of course, we try to maximize what the delta T that is going to the power cycle, that at least minimum is 150 degrees C or maybe 200 degrees C in order for it to increase that efficiency of the power cycle. And what we have is a lot of different targets, as you can see. So I'm going to be discussing today is for the thermal energy storage. That is in particular how I'm working on this area. And it is this one here. Well, it's not just the thermal energy storage, but that is in reality what is that additive manufacturing can be utilized in the heat exchanger that goes here to the power cycle, that is between this fluid and the supercritical CO2 power cycle portion. This heat exchanger has a lot of opportunities for 3D printing. And there are some for the receiver. Those are something that we need to discuss because, as you know, the printability, it is not just about the material, but it's about the design that you can efficiently print. Here is for the third generation, there were 3 different pathways, and that depends on the solar receiver design. Those were for liquids, solids, and gas. That is the fluid that is utilized to absorb that energy. And of course, here are the challenges that we have for each of those. So for this one, the solar office was focused on trying to optimize the receiver, the storage, and the heat exchanger. So in these two, the receiver and the heat exchanger is where we have opportunities. But they selected right now to go to a demonstration that is at 10 megawatts for the solid particles. There are still some challenges in the liquids. That is still the liquids is the same, similar to the second generation that is using molten salts, but there are still some challenges that we need to mitigate in order for these plants to be I would say from the market, from the market point of view, for for the banks to feel comfortable that it's going to be provided all the amount of dollars that are needed to these the capital cost that is for these big plants. So here I'm not going to go too much to on this. Is what we are trying to do here is what is that I can utilize with advanced manufacturing. What I need really is to demonstrate that I can have a low cost fabrication and with a long duration, that I can extend the duration, because there are certain mechanical problems that might be occurring due to the conventional manufacturing of those parts, that I'm trying to say that if we go into additive manufacturing, we can extend the duration or the durability of these components. Of course, everything is to, you need to show that there is an economical benefit doing this. You have to show the feasibility of the technical feasibility of that approach, but it has to be economical. If it is not economical, it is very difficult to be deployed and implemented. But all of these that we are learning right now for these type of technologies is not only for concentrating solar power for the production of electricity. We can also use those approaches for solar fuel synthesis and sort of also desalination. So the two big portions that I want to discuss here is, for the project, I need to do a validation of the technical feasibility of this advanced manufacturing, because we need to keep the capital costs at reasonable market levels. The way for us to do that is we have to do physical metallurgy and thermomechanical validation of these approaches for the advanced manufacturing, and also their welding. These are very big components, so I cannot print the whole component at once. So I need to be printing. I can decrease the amount of connectors, and that's the objective, but still I will need to be welding some parts. And the welding of one 3D printed part to another 3D printed part is being evaluated in our project. But also one printed part to a broad alloy is also being evaluated to determine if there is any part in the welding phenomenon that can decrease the strength of the component. So here, what is important that I'm saying that is that we can minimize the machining and the welding time compared to conventional manufacturing. That's how I'm trying to sell that when we're trying to go with advanced manufacturing like a 3D printing, what is that benefit that is getting me against the conventional manufacturing? It's not just cost. It is the extension of the lifetime, because I'm minimizing the amount of weldings and connectors. And when we're talking about very high temperatures, minimizing the amount of connectors is big, the opportunity that we can have here. And what we're doing is validating that additive manufacturing for intricate designs for the primary heat exchanger and the solar receiver. And what we are trying to do here is evaluate the mitigation of the crack susceptibility. So here is what I'm doing in the project is just, I have certain design of the CSP component, like the solar receiver and the heat exchanger. And then I'm using the additive manufacturing in combination with conventional manufacturing for some cases that the additive manufacturing cannot print that part like a small tubes with 1 inch of diameter. And I'm using in my project two different approaches. That is the laser powder bed and the electron beam additive manufacturing. And that's going to be for the integration of the CSP for all of those components. How are we doing this optimization? We are utilizing the finite element modeling, and also we are doing techno-economic analysis to really optimize what is needed here for the increased feasibility to be adopted. And we are also evaluating designing the similar and dissimilar welding. I'm going to explain later what is that I'm trying to do with the additive manufacturing to see if we can combine similar and dissimilar alloys in that portion, in the heat exchanger. So here, what I want to do in order to increase the performance that I need is to yield a plant lifetime. They're looking for 30 years. This is probably sometimes it's too dramatic to really go to 30 years, but if you can really have a cost-effective, maybe 10 years or 15 years that you need to replace, but it still is cost-effective, that is something that we can, of course, have it will have an opportunity. So what we are doing is doing experimental work using validation of those models. We are evaluating the crack susceptibility. We are evaluating the weldments. We are also evaluating the failure mechanisms that we can have. And we are using the Global simulator to really grab the data. And that all here is to validate the feasibility of this. The other portion that is needed is we need to design and optimize the dissimilar welding. Why? Because there are some combinations that because of the high temperatures, and also these plants, they go daily with a thermal cycles that you need to go daily when the sun is up. You can reach in the receiver temperatures, probably the skin temperature can reach up to 800 degrees C, but you know that you're gonna be at the heat exchanger at 720, the delta T is gonna be 720 to 500. So that is gonna be always a thermal cycle that the system is gonna be seeing while it is in the production of electricity. But also when the sun is down, some parts can go to drop the temperature dramatically. The receiver, since it is exposed to the atmosphere, it will drop to room temperature. There are others that we put, of course, they are isolated, and for example, the heat exchanger will see only probably a delta T of that 150 degrees C. So what we have to do here is predict the material's lifetime based on the creep, the thermal fatigue, and the susceptibility to cracking. So these are evaluations that we need to really validate and confirm that we are going to be extending the lifetime of these new components. And the other portion that is extremely important for us is the techno-economic analysis. We need to include what are the materials cost, the processing, and the reliability. If we can determine how we are going to be impacting the techno-economic analysis by increasing the reliability of the plant and the availability of the plant. What is the meaning of the availability of the plant? If I don't have a downtime for the plant because I need to do some repairs, or because there are some issues that I need to take care of, or dropped the temperature, probably stop the production of electricity, I'm losing money here, right? So that is going to be impacting also the techno-economic analysis. So if I can put a number on how I'm increasing the availability of these plants, it's a highly feasible approach that we can have for the deployment of these new technologies and advanced manufacturing. So here in this slide, what I'm going to be showing you, in general, you might know because you are here about understanding or wanting to learn a little bit more about the advanced manufacturing or 3D printing, are the benefits that why we're exploring these routes, right? So in the 3D, in the generation 3, the delta T, or the temperature for the production of electricity in these plants, is between 500 and 720, or yes, it's about 200 degrees C. And they're really going to a lot of thermal fatigue and creep fatigue, and also creep is important. So what are the advantages that I'm trying to have here? I can have a low material waste. These alloys are extremely expensive because I'm trying to have nickel superalloy because of the extreme temperatures that I need to go. So just by decreasing the amount of materials that I need, I'm saving here. So also is the fast manufacturing process. This, if I can show that instead of needing a year for the fabrication of the plants, these can be reduced half of the time, let's say 6 months, is a lot of money that I'm saving. The high quality and the low volumetric defects that I can have with this, I have to prove it and show it and validate this. The flexibility that I can have here, combining these similar alloys in the same process, is something that I would like to explore to see if there is an advantage when I try to incorporate different materials here. I'm trying to minimize the post-manufacturing processes, but in some cases we need to do some heat treatments that is necessary, but depending on the size of the component, that will require what are the size of those furnaces that I need to put in there, and everything is a certain amount of dollars that I will need for this. Something that is important is, as Jacob said before, is like we can print certain designs that are impossible through conventional manufacturing. And also the part combination and reducing, because you're reducing joinings and you're reducing the connectors that you need in here. So when you are doing this, you are really increasing the reliability of the long time of these type of components. And I'm trying to also remove certain bulk sections that you need to really combine. This is a combined effort with the design of those parts with the benefit that the 3D printing will give you. So we have to really work pretty close with the designers in order to see how we can optimize this type of designs with the advanced manufacturing. At the end, what I want is the cost reduction at the capital investment level. I want also to reduce the operating and maintenance costs. This is extremely important. And the cost reduction also by increasing the plant reliability and availability. That is means the reduction of the plant failures. So here is just all the alloys that we are investigating for this Gen 3. There are certain alloys that are, these one are the high nickel alloys. There are also some others that are steel with special alloys, and there are also some stainless steel that you know about them. Also, we're exploring the P91 and P92. So here is the list of some of those that we were exploring at the beginning for the liquid, the particles, and the gas. And these are the list of the alloys. So far, these are because they, for example, for the liquid, they need to be corrosion resistant to the molten chloride. The other ones for the particles, this is depends on other consideration that we need to have for particles, and they are very small particles that are flowing in the system. And for the gas, in the gas we have helium and supercritical CO2 that are part of the gas that we use as a fluid. But if you see the common here is the Haynes 230 and the Econel 740H in all the three. Why? Because they are giving you the creep and fatigue for at the high temperature. But we know that Haynes 230 is difficult to print. That we demonstrated that with some two projects that we have, one with Elementor 3D and another one with UC Davis. The ones that are closed and are really also good and can print pretty well is the Haynes 282 and the Inconel 740H. These ones here are for the low temperature. And the C22 is pretty good with the corrosion, with the molten salt. And what we would like to see, can we use the C22 in one of the end portion of the heat exchanger that is going to be exposed at 500 degrees C, and probably on the other end is, can I have the Haynes 282? Everything, all the crazy ideas is if I combine and try to use less of Haynes 282 instead of this one, I use the C22 alloy. Can I drop the cost of the component? Those are the questions that we always have. So I will go very quickly with this one. See, these are all the considerations that we also always take is the yield strength, the ultimate tensile strength, and the ductility, how it's being affected, but these are for broad alloys. So we have to evaluate what is happening with the change of properties once we print them. And here are what we say, for example, if I say that the Haynes 240H is the best alloy for me based on cost and properties, what are those that I can have as being considered that are in the rank here, or that I say that they might not give me, they don't give me a good yield strength, so they are below the 740H, that is the one that I'm having as the baseline. So here are some of the hot candidates. Hot candidates for me is for 720 degrees C, and the cold side candidates are for 500 degrees C. So for this one, I'm considering what are the properties or those alloys that I can use based on the CTE. And if I'm combining this one with this one, I'll try to match the CTE that is coefficient of the thermal expansion. In this case, I'm showing you what is the rupture up to in a range of 100,000 hours. And this one is the clip rupture for, in particular, our nickel-based alloys and the austenitic and ferritic alloys. So in here, I see that, yes, Inconel 740H and the Haynes 282 are the top alloys for the high temperature. And here is also some of the properties that we consider when we are evaluating or doing the down selection of those alloys is for the corrosion behavior. What are the corrosion behavior of those alloys that I'm considering? And for, depending on the temperature, what is the corrosion rate that is in micrometers per year? In this case, I'm trying to be below 20 microns per year, at least if I'm considering that I want to have a 30 life stem, 30 life of the lifetime. So here are the alloys that we said that are the top, were the top alloys, the Haynes 230. This one is also the Haynes 282, has a similar behavior. Then we said this Hastelloy 276, but the Hastelloy 276 might have a sensitization after you have the welded the fabrication of the C276. And then we said that C22, the Hastelloy C22, is very similar in the behavior of the corrosion behavior as the 276, and it will give me a more reliable and the feasibility that no metallurgical changes during operation or probably during the fabrication and post-fabrication. And the Inconel 740H is still one of the top alloys that we're considering. And at the end, what I wanted to show you here is what is that we also consider? Well, we'll have a relative cost. Of course, this is at the material level. There are a lot of other things that I said before for the techno-economic analysis that I'm considering. So if I take the Haynes 230, that was the original alloy here, that is up one. So I'm gonna be comparing everything in the cost per mass. How many times the other alloys are more expensive or less expensive than Haynes 230. So in this case, you see that the 740H is a little bit better from the material cost only point of view. And that's why we are considering how can I really use the 740H that is giving me very good results and from the all the properties that I'm evaluating. And the other one is the C22. There are others that are like these ones, but they are not giving me a better corrosion evaluation, corrosion resistant, and also fabricability, metallurgical changes when we compare that one with the Hastelloy C22. So the top alloys right now that that are my top alloys are this one, Haynes 282, Inconel 740H, and the C22. Those are my top alloys that I'm evaluating right now in the project. So at the end, as I said, this is just the beginning that we say what is the down selection of some materials that I can explore. But then at the end, I need to really compare with these alloys that are already down selected, do the full techno-economic analysis. In that case, I need to consider everything. Everything that is in particular the fabrication, the post-fabrication, and everything that it needs to be there in order for us to say that is very feasible and it has a good opportunity for deployment. So with this one is the end of my presentation. And this is again a photo of this humongous plant that you see here are the tanks. They are 40 meters diameter, 15 meters tall, and this is 200 meters is the tower. And the tower and here is the solar receiver. So with this, I'm open to question if I have time. If not, I can just move this to the end.
Yeah, I really appreciate that. I'll start with a question while some of the other questions are coming in here. I recently saw, and you've been hearing about these sorts of technologies and concentrated solar power for quite some time. What are some of the differences recently? Why has it become something that I've now seen a number of different conversations about concentrated solar power? Has there been a technological leap?
I don't think that I understand the question, Jacob. You said that why recently?
In the past, it seems like concentrated solar power was dealing with like 400 degrees Celsius. Has there been a significant leap in the temperature that these solar panel are these not solar panels, but these concentrated solar power plants have?
Okay. I understand. Yes, I understand. I understand. Yeah. Okay. Very good question. The plants that are already in operation, they are operating at a 5 and 65 degrees C. Those are the second generation. So in the second generation, of course, there are opportunities as well in order for us to increase the lifetime. Those plants, they have, I will say, 8 years in operation, or maybe 10 years if we consider the 20 megawatt of the pilot scale plants, and now the solar, how we call the Crescent Dunes that is in Nevada. Those are humongous that are I think that are 200 megawatts, and they are operating with the molten nitrates. Molten nitrates can give you you can work up to 565, not above because it will decompose. And that one is they are the ones in operation. And those are also other opportunities that we have. Yes. Why? Because the primary heat exchanger is having issues. And those issues might be related with the fabrication. We need to explore what the issues are. Can we really increase the reliability of these components by going into 3D printing? The alloys that are being printed, or the alloys of construction for the heat exchanger is, it might be, I don't know if it is a nickel alloy, but or is a 347H steel. So of course, because of the temperature, we can use other alloys. And there are opportunities there as well, because I'm having other projects in which we are trying to, there are some problems with the tanks that they're failing, and the failing is due to welding. So welding is something that we need to pay attention. We are metallurgists, maybe most of us that are here, and we understand that that is not an easy peasy portion that you put just a welding and then you join them and that's it. And there are some standards that says what are the filler. No, that is not really that easy. We were seeing issues with the filler, and now we are changing the filler. That's part of one of the projects that I'm working also with Colorado School of Mines. That it says the filler that it was used before is not reliable. It is really providing some problems here. So let's change the chemistry of the filler in order for us to avoid some of those thermomechanical failure that we are seeing right now. It's not about the corrosion issues. It's not the corrosion issues right now. It's the thermomechanical issues that we are seeing right now. So this is about the fabrication. How do we fabricate them and minimize all the metallurgical changes that are occurring with time? So, and this one is because if you increase the temperature of the power cycle, you are increasing the efficiency of the production of the electricity. And then you can be more cost effective. That's why the US is pushing to the third generation. And it's because by increasing the temperatures to that level, of course, we need to go now to a more expensive alloys. That's why we are trying to drop the cost if we can with the fabrication of those components. But we need to work with nickel superalloys. And it's because we're increasing the power cycle efficiency, and thus we might be able to have the 5 cents per kilowatt hour goal. You're mute.
I think this relates back to a question, or a couple questions that I've seen now about, when you are going to these kind of wild temperature swings from when the sun is shining to when it's not, how do you control for, you have great properties at high temperatures, but what happens when it's cooling? What happens when you're changing temperatures so wildly and so quickly?
Mm-hmm. There is a lot of work ongoing. In particular, for example, Idaho National Lab, they are exploring and evaluating the thermal fatigue and the creep fatigue and the creep of these alloys. And they are evaluating, for example, the Inconel 740H is pretty good for those conditions, and the Haynes 282 is pretty good. So if you see, the plant will have a different operating conditions, completely different. If I'm considering, for example, the heat exchanger is always going to be between 500 and 720. But the one that is really very going from room temperature to 750 degrees C daily is the receiver. So that's why the receiver is the one that have a particular design depending on the thickness of those tubes that are having the fluids going through the receiver. And that's why, based on the design of the receiver and based on the fluid that you are, the properties of the fluid, like the heat capacity of the fluid, how fast you need to move that, what are going to be the hot spots or the skin temperature. A lot of those are being evaluated through design to see what is the optimal design that you can have a 90% efficiency of the receiver, and that also the properties of the alloys going to 750 and the room temperature 750 daily, because it is open to the atmosphere, or is very extreme. So that's why the considerations that we use for design, materials, fabrication approaches are completely different when we consider the receiver compared to the heat exchanger. So that's why for us at the 3D printing opportunities, I think that we have more opportunities at the heat exchanger than at the receiver.
Sure. Okay, well, yeah, I really appreciate that. And as more questions come in, certainly we can address those at the end. Yeah, I'd like to thank you again for joining us and presenting here. Certainly, I think this is interesting work. Yeah, thank you, Judith.
Thank you.
Okay, next up we have Greg Chitwood.
Yeah, just let me pull up my second screen here. Okay. Thank you for the opportunity, Jacob. Can everyone hear me?
I can, and I can see your presentation.
Cool. All right. Good. Awesome. Thanks. Hello to everyone. I just want to give you a brief snapshot of Bühler's nickel alloy production because I think it gives us a good foundation for the nickel powder that you'll hear about and that Bühler provides for additive manufacturing. First of all, Bühler is a very old, established company, no matter how you look at it. I've seen this plaque, which you're seeing here, on one of the buildings that commemorates when metalworking first began at this site. It's a strange way of writing 1446, and that's nearly 600 years ago. These were Renaissance times. In Austria, iron ore was being smelted in rather small, crude furnaces called bloomeries. Most of the iron production went into armament and weapons. Although Bühler as a company didn't formally exist until about 150 years ago, which is still a long time, you can say that steel and metalworking are in Bühler's DNA. That's why I show the DNA strand there. Today, the company is quite large, as you can see in this photo at the right. It goes approximately 1 kilometer from the buildings in the foreground all the way to the far back. This slide gives Bühler's statistical data at a glance. There are 2,260 employees producing approximately 124,000 tons of steel annually with a turnover of about 600 million euro. Nickel alloys must be produced quite differently from steel. Whereas steels are typically made from iron ore in a basic oxygen furnace or from scrap in an electric arc furnace, modern nickel alloys for the most demanding applications are melted in a vacuum induction furnace and then remelted in either an electroslag remelt furnace or in a vacuum arc remelt furnace. Bühler produces thousands of tons annually of nickel in this way in about 20 unique grades, 718 being one of them. Bühler currently has one VIM furnace, and that VIM furnace feeds 11 vacuum arc remelt furnaces, 10 electroslag remelt furnaces, and 6 specialized ESRs known as PESR, that's pressurized ESR. PSRs can remelt certain materials under nitrogen pressure in order to boost the nitrogen for increased strength or corrosion resistance. All production, from melting through forging and on to heat treatment, is done in Kappenberg and Deukendorf. These sites are physically separated, although by less than 5 kilometers, and that's why Bühler often talks about its production basically being in one location. This is very important for the technical and quality control. So 718 is double melted. Why do this? It is essential to the quality of high-strength nickel alloys to double melt them under vacuum or protective slag. Without double melting in this way, exposure to the air would lead to unacceptable oxygen, nitrogen, or hydrogen contents, and these could result in poor ductility, low toughness, or reduced fatigue strength. Mills that are serious about providing nickel alloys to critical applications in aerospace or in oil and gas or power generation use vacuum induction melting and remelting with VARs and ESRs to reduce these harmful gases to the lowest possible levels. Well, additive manufacturing can take advantage of this too. Even though the printing takes place under the cover of inert gases in additive manufacturing, the additive manufacturing process itself cannot clean up an already dirty microstructure. This is why Bühler's nickel powders for additive manufacturing are double melted. Here is a complete schematic of Bühler's bar production route. Nickel alloys are melted in a special steel plant here with a VIM and either VAR, ESR, or PESR. The nickel alloys actually just get VIM or VAR or ESR. And then they're hot worked through either forging or rolling operations, and then heat treatment. Then on to machining. The machining is used to produce a bright surface finish and material that's free from any surface defects or contamination. And then finally, they undergo testing and metallurgical testing and quality inspections before shipment. This slide highlights some of Bühler's key industry approvals. I'll point out that for 718 with 150K yield strength, which was a specialized heat treatment developed in-house at Bühler, this alloy received NACE and API approval for oil and gas in 2018 and 2019. However, really significant is in aerospace is the approval to produce rotating parts quality, which means for jet engine components. And this is one of the most prestigious accomplishments there is. This doesn't take place without demonstrating the ability to provide the utmost quality and consistency in steel making. Bühler doesn't stand still or rest on its laurels. Just since 2016, when I started consulting for the company, there have been significant investments in plant and in equipment. 2016 marks the building of the powder facility dedicated to additive manufacturing powders. Entirely new facilities were also built for the chemical laboratory, for the P44 rapid forging press, and the new steel plant, which you see here in the foreground of this picture at the lower right. This new steel plant is a 350 million euro investment in a state-of-the-art facility, which will be the most advanced of its type in the world when it goes into service next year. While this plant doesn't produce nickel alloys, nonetheless, it represents Bühler's commitment to being a leader in special steelmaking industry. I'll leave you with this slide. It shows again the general production overview and includes the powder production at the lower right over here, which is much simplified compared to the rest of the production in the facility. Thomas will talk more about the powder production in more detail. So thanks for that opportunity to give you a brief snapshot of Bühler's bar production. And I'll take any questions if there are any.
Yeah, a quick question here before we go right into Thomas's. Which raw material are you using? Is it virgin charge? Is it mill scrap that's used for producing the nickel alloy powders?
Well, the nickel alloy powders are first made in the bar route. Thomas will go into that, I think, in more detail, but we start with charge for our powder production that comes off the VIM furnace that would otherwise be used for the nickel alloy bar production. Now, that particular charge is made up of nickel scrap and nickel pellets and alloying elements that are purchased, for that particular purpose.
Okay. Let's go ahead and jump right into Thomas's conversation, and then we can answer some questions, because his presentation might answer some of these questions as well.
I think it will, yeah.
So Thomas, I'm going to hand it off to you.
All right. Can you see my presentation?
Yes, I can.
Okay. Well, thank you for having me, and I will give a short introduction about our powder production, and then in the end also about our special heat treatment we achieved with our Inconel 718 AMPO powder API. So let's jump right into it, into Bühler's approach in additive manufacturing. So how come Bühler produces powder for additive manufacturing? Well, we have a long history. We have metallurgical and material know-how for centuries, as Greg pointed out already, and also for nickel-based alloys in highest quality since 2000. And also we have a know-how in powder production with our powder plant, which we have now for over 2 decades. And well, combining these two, there's only one step you can go ahead, and this is actually producing powder for additive manufacturing. And to follow up on Greg's presentation, you have here our whole production roadmap. With the lower right side, you can see our AMPO production. And well, basically, having a whole steel mill in your back, it's easy to get to your steel grades and also your nickel grades, of course. And this makes us easy to produce different grades, and we can choose from which side you want to have. Like we can get from the special steel plant, which is our VIM, so vacuum induction melting, but also from our electric arc furnace, so EAF. And well, we can just go to our stock, and then we can get our feedstock from there as well. And Next thing is there are different types of powder, as you may know. So there is a water atomized powder, gas atomized powder, and also plasma atomized powder. And you can see here an increase of sphericity from left to right. And we here at Böhler Edelstahl, we can produce the gas atomized powder, which excels with high sphericity as well. And to give you like a more detailed overview about our atomization process, we're here in the melting and atomization step. So basically, what you have here is you have a vacuum. So you melt your metal in vacuum, and then it gets atomized with an inert gas. We use argon gas for this. After that, we make sure for highest quality. To achieve highest quality, we have a sieving and air classification step, which is also done under argon gas. So you have the protective gas as well, and also it gets packed under argon gas. And we also do, of course, after every batch, we do internal testing where we test the chemistry, the PSD, which is the particle size distribution, the flowability, apparent density, morphology, and so on. So to get to our atomization systems, we have on the one hand side we have the VIGA, which is the vacuum inert gas atomization, which is basically for iron, nickel, and cobalt grades, so non-reactive metals. Here you can see the melting chamber, which fills the molten metal into the tundish, which you can see a more close look here. You can see that this molten metal is in contact with the tundish. So then it flows down into a so it flows down where it then gets atomized with a closed couple nozzles where argon gas comes out, and you receive the powder. And on the one hand side, on the other hand, we have the IGA, which is the electrode induction gas atomization, which basically looks like this. This is especially for reactive metals such as titanium or columbium or molybdenum. And the difference here is you don't have any contact from the liquid metal to a tundish. You actually have an induction coil which melts this bar material, and then with this, as it pointed out already, with this free fall, you have the nozzles down there, and then you achieve the powder by blowing inert gas into this free metal metal free falling. So afterwards, there's the powder classification step, and here we have a short video. I hope you can see it. First of all, we have this sieving step. Afterwards, we have this air classification step, which is combined. And of course, this is under a protective argon gas atmosphere. And basically, what we achieve with this step in particular is that we separate the coarse fraction from the fine fraction. So you can see this whole step is based on the mass of the particles, and on top you get the fine fraction out of it, and on the bottom the coarse fraction. So to give you how we describe actually a powder particle, there's the chemical composition, the particle size distribution, as well as the morphology. So you can see on the right side we have the PSD on top, and then a few morphology pictures from SEM on the bottom, out of a SEM on the bottom. And this leads to our resulting properties being flowability of the powder, apparent and tap density, humidity, and the oxygen content, which we can measure as well. So then now I will give you kind of an overview about how important each and every step can be in 3D printing. because this right now is basically, especially for the heat treatment. First of all, we did this with our L718 AMPO API powder, which is the Inconel AMPO, which is the Inconel powder. And there is a difference between the API powder and the normal AMS powder, which is basically the columbium content, with the L718 AMPO API having a lower columbium content than the normal AMS standard. And normally in the oil and gas sector, you go with the standard for 120 KSI, but with this heat treatment, we achieved 150 KSI, not only for bar material, but also for our AMPO powder. All right, so here you can see the temperature time curve. And basically what Böhler tried here with this heat treatment is to get the best of both worlds. So first of all, we have the solution annealing according to the API standard, which is done at 1021 degrees C to 1052 degrees C for 1.5 hours. Why do this? Well, you want to get rid of your secondary phases, which have a bad influence on your toughness and also on your corrosion resistance. Basically, these secondary phases, especially the delta phase, cannot be in the material matrix, so it goes to the grain boundaries, and there it has a bad influence, being really brittle, and also decrease the toughness. You get high strength out of it, but it decreases toughness and also the corrosion resistance. And after that, you proceed with water cooling, and then you get the aging according to the AMS standard. It's a two-step aging, as you can see here. And with all of this, you can achieve high strength. So you can achieve those 150 KSI. And yes, everything is done here under an all-air atmosphere. And on the right-hand side, there's a picture of the microstructure of this printed and heat-treated part. And you can see here there are clean grain boundaries in an austenitic microstructure. So you don't have any presence of these secondary phases. All right, and then we made a short density testing plan where we did density analysis, and also we compared the mechanical properties from the as-built to the heat-treated state, where we did tensile tests, Charpy impact toughness test at -60 degrees C, and also hardness test with HRC. And here you get the summary of these mechanical properties. On the right-hand side, you have the standard, so the API standard 6 ACRA, which is basically for the bar material, 150 KSI. And in the middle, you have the as-built vertical and horizontal values, as well as the API 150 KSI vertical and horizontal values. We need to say that this powder and these samples, these testing samples, were printed on an EOS M290. And as you can see, when this heat treatment is applied, we are well into the standard range. And of course, you need to consider that this is in megapascals and not in KSI. But basically, 150 KSI is 1034 megapascals. So we are well into the 150 KSI range. So we achieved the yield strength and also the tensile strength with having already with the elongation reduction area well into it too. And then if you go to the tested to the Charpy tests, you can see that we achieve high toughness as well. So we have on the one hand side we have really high strength, but also high toughness with 63 to 67 joule for an average of 3 samples. And with the hardness, we are also into the in the standard with 44 HRC and the standard deviation of 1. HRC. So in conclusion, you can say that this L718 AMPO API showed good printability. The mechanical properties, if you compare it to the API 6 ACRA bar material, you get you can reach the tensile and hardness properties of the bar specification. The impact properties at -60 degrees C are very high. So as I pointed out, between 63 and 67 joule. The impact values for longitudinal direction of bar specification are nearly reached. However, this is not really important when it comes to industrial standardized tests. So yeah, and you always you have to consider that this API specification is developed for bar materials and not for AM products. So we can achieve this standard, which is made for bar materials with our AMPO, so with our AM powder. And in the end, with the microstructure short conclusion, the grain size of bar material can be reached. And of course, that the AM printed specimen, they show a finer grain size than the bar material. And in the end, you will end up with an austenitic grain size with no presence of any secondary phase whatsoever. So here on the right-hand side, you have a nice overview about the bar material on the left side and also the AM printed on the right side. I can see the austenitic and microstructure and also the twins. All right, so that was it from my side. Thank you very much. And if there are any questions.
Yeah, so I think we're getting a couple of different questions about the corrosion testing that you've done. Have you gotten into corrosion testing yet on the L718?
No, not really actually. You can, I mean, you will basically have the same the same properties as the normal L718. So we did not follow up that much on that. Yeah, and also, if I can add something, it's really important how you print your part. So basically, when you have like a bad parameter set, then you will end up with a lower corrosion resistance than printing it with a good parameter set, of course.
I know for us at Elementum, when we've done any different corrosion testing on additive manufactured materials, we see some benefits to the printing process, but we also see some drawbacks. Certainly the smaller grain size typically would mean that you have a higher volume fraction of grain boundaries, which means then that the attack is a little different, but it's the same as if you just had a smaller grain size material. So yeah, we've seen at Elementum some differences when we've done some corrosion testing, but not massive differences.
Mm-hmm. Okay.
We had a question too about what machine was used to print the material. It was, I think you mentioned the EOS M290.
Yeah, the M290. Yeah.
Have you printed in on any other printers as well, or the M290 only so far?
No, the M290 only.
Well, that's just for the 150 KSI material that you saw there. Yeah. I think the 718 has been printed on a number of different machines. Just this particular data was for the with the M290.
Sure.
Yeah. So we did this at the voestalpine Additive Manufacturing Center in Düsseldorf, where they helped us with the M290, and just to achieve this 150 KSI.
Okay. Let's see here. So what other nickel alloys do you produce there at that facility? Are there other? I know 718 and 625. Are there some other nickel alloys that you've produced at that facility in powder form?
Yes. We can also produce the Hastelloy X. Yeah, I think it's the same in America, right? It's LOX. So yeah.
Right, and we would have capability of producing pretty much any of the nickel alloys because the melt volume is fairly small. For us, since we want to use product, the input stock being from our VIM furnace, you know, I'd say we would be able to easily offer among the 20 grades that we currently have in our catalog of nickel-based alloys. You know, most of these are precipitation hardened alloys because that's kind of what our specialty is. But we could do, you know, any one of those fairly easily. It's just a matter of really commercial interest, I think. And then we would certainly want to make sure that we are getting the properties that you'd look for in terms of powder size distribution, particle distribution, you know, the flowability and all those kind of properties. So, you know, it's not something we would just turn on and start doing next week without putting some careful thought to it.
And then I've actually gotten a number of different questions about the oxygen content. You mentioned you're monitoring the oxygen content. Is there something you're looking for that's typical, or is there something that would indicate that a product is no good? That's some of what we've seen at Elementum as well, is that you may be able to collect data, but do you have some indicator as to what would make a product not pass inspection as far as oxygen or humidity or whatever else is concerned?
Yeah, of course. I mean, you have specifications with typical customers, or you have your internal specifications, of course, as well, where we say from Böhler now that this is not good to give to a customer, because if you print it, then the oxygen content might be way too high after the first print job, or yeah. So basically, we are working on that with our AMCs to get more and more information about it, and yes, so to be sure that we don't make any mistakes with oxygen contents, because yeah, I mean, that's basically it. Yeah.
Okay. So you know, there have been a number of other different conversations and questions that have been coming in, but I do want to make sure that we get Judith back in the conversation as well, in case there's questions there. And then I think we're about ready to wrap up here. What other kind of investigation have you done along these lines? Have you been able to jump into like doing different backscatter, SEM, TEM, different looks at chemistries and distributions of those chemistries? Do they look typical? Do they look different from forged or machined or investment cast product?
Well, first of all, we are a powder producer, so basically with those with the printed parts, we don't have those test results, and yeah, so we don't have like an EBSD or something like that.
And
this was sorry, Jacob. This was also not the scope of this investigation, because we wanted to achieve with our powder this 150 KSI standard.
Yeah, as I was going to say, at Elementum, we do have some of this. A lot of these are, you know, trying to compare additive manufacturing to additive manufacturing. So there's still a fair amount of work to be done on comparing additive to a standard cast or forged, and what the microstructures might be and how they might behave differently. So there's still a lot of work to be done. I think we would all agree with that. But I think there has been a lot of progress over even the past 12 months, which I think has been really exciting for nickel superalloys in energy, in power generation, in and in other fields as well, and in oil and gas, mining, renewable energies, all sorts of things. So it's exciting.
Mm-hmm.
Yeah, I'd probably like to say that as far as oil and gas concerned, The oil and gas industry is very conservative. They want to very carefully evaluate things like the corrosion resistance and the environmental cracking resistance before they step into it. And so as far as looking at different, different compositions, we see that additive manufacturing could eventually give some really important advancements in that area, that you could tweak the chemistry based on the fact that each particle that's being solidified in the atomization chamber is essentially its own ingot. So you get a lot of benefits that way in terms of microsegregation and chemistry control over a very narrow distance that forged product might have trouble with. But with the conservative nature of oil and gas anyway, I think where the industry is right now, they're really trying to compare additive manufacturing to conventional manufacturing. And so we're kind of at this stage of looking at this very strict API composition of 718 additive manufacturing and how that compares to what we know and have 15, 20, 30 years of experience with. And,
I really do feel that there's some significant advantage to being able to create heat exchangers, being able to develop manifolds and different ways of routing fluids that, aerospace, also being a conservative industry, has been able to overcome some of these questions. But I think the questions that we're asking for oil and gas and for renewables as well are questions that take longer to answer, even if the amount of data might be the same. Corrosion testing and development of those types of corrosion fatigue and different types of corrosion testing are difficult to test for and take a long time. So we're starting that element, and I'm sure there are others here who are participating in this webinar who are also working on it at the moment. But yeah, I think there's still ways to go. Okay, are there any closing comments? I'm gonna hand it to Judith if she has any closing comments, and then we'll go around. So Judith, anything to add?
No, I completely agree with you. There is still a lot of information or data that we need to gather in order to convince those that would like to implement or use these type of approaches. But I think that the way for us to accelerate this is all of us working together, experts in that area, and being helped by my models, that we can probably have some background mechanisms that we need to really validate and try to foresee or try to see what will be the expected behavior after a certain amount of time or under certain conditions. What are those conditions that will make it fail? So it is extremely important that we as a community, working with universities and companies like yours and national laboratories like us, we can all collaborate and have the data pull it, to move faster, because I think that we don't have that, too much time. So we need to really move fast.
Agreed. Greg, any closing comments?
Well, yeah, I'd say that first of all, I'm very encouraged to see that the properties, the microstructure, for instance, the 718 can equal those of the forged product. Particularly the microstructure is super important, because in oil and gas, we know really it's all about the microstructure in terms of environmental cracking resistance. So while we don't have that data yet, it's coming as far as the environmental cracking resistance. I'm encouraged about what we're seeing here.
I agree. And Thomas, one quick clarification before your closing comments. Bowler is using gas atomization, and specifically which atomization process?
Well, both. I presented both. So we have the VGAS system and the IGAS system.
Okay, so both of those, but no plasma atomization at
No
both?
planned conversation, no.
All right, and any closing comments from yourself, Thomas?
No, actually not. Yeah, thank you for having me. And yes, so I can only agree on what Judith and Greg said. And yeah.
Great.
Thanks
Well,
so much.
I'd like to thank everyone. I'd like to thank all of our presenters and everyone who attended this meeting. Certainly, if there's, I think there'll be the presentations will be available, I believe, and we can confirm and then share that with anyone who reaches out if we don't share it otherwise. So, if you'd like any additional information or if you'd like to reach out to any of our presenters today, please feel free to reach out to me at jacob@elementum3d.com, and I'd be happy to pass along the contact information so that you can talk with any of our presenters that presented today directly. Yeah, so thanks everyone. Have a good rest.
Bye.
Thank
Bye-bye.
you. Bye.
Thank you.
We're done, Thomas.